Okay, now I have added some figures, so I'll go back and look at the topic on streamlines in some more detail, and then I'll talk about relative streamlines. Okay. Now consider a curve in a three-dimensional region of space. We can describe the curve by the parametric equation, the position vector r equal to function of r of s, where s is the arc length. So this r of s is xs ex plus ys ey plus zs ez. Now consider a curve. This need not be a streamline for the timing. It is an arbitrary curve. Okay, so I've shown a coordinate system ox, y, z. Suppose I have a point P which is fixed, and I consider a sequence of points on the curve in the neighborhood of the point P. So I have labeled 4 of them as Q1, Q2, Q3, Q4. So I'm moving from Q1 towards P. Okay, so that if I look at the distance along the arc between P and Qn, it will decrease. So I can talk about the position vector of the point P and the position vector of the nth point Qn. Okay. So consider a sequence of points which are labeled Q1, Q2, Q3 on the curve in the neighborhood of the point P, such that the chord length delta Rn approaches 0 as n goes to infinity. So by chord length, I mean the length of these vectors P. So if I want delta R1, it is the length PQ1. Okay. So I can talk of a displacement vector which is PQ1. Likewise, I can talk about another displacement vector PQ2. Okay. So delta Rn is PQn, the nth one. And if you look at this vector triangle, let us look at Q1 first. All right. We see that OP plus PQ1 is OQ1. Therefore, PQ1 is OQ1 minus OP. So I can write PQN as OQN minus OP. Now OQN is the position vector of the point Qn. Here you can look at 1 or 2 or 3, whatever it is. And OP is the position vector of the point P. So I can write it as R of the nth point Qn minus Rp. So the length of this vector delta Rn is the chord length between P and say Q1 or P and Q2 and so on. So I've taken a point P which is fixed. Okay, I've started another point far away from it, Q1, and then I'm taking a sequence Q1, Q2, Q3 and so on, such that the length of the chord keeps on decreasing. Okay, so what you observe is that as the points Qn approach Q, this displacement vector becomes tangent to the curve. Okay. So the important thing is that as the magnitude of the chord length, delta Rn vector magnitude goes towards 0, the direction of the displacement vector delta Rn approaches the direction tangential to the curve at the point P. So this you have to see from the geometry of the figure. So, now consider the arc length along the curve between two neighboring points with position vectors r and r plus dr. Okay. So if r and r plus dr, if dr is an infinitesimal increment in r, okay, then the magnitude of dr is nothing but your ds, the arc length. And this you can write magnitude of dr as square root of dx square plus dy square plus dz square. So if I look at the magnitude of dr ds, you see that it is 1. Okay, because dr magnitude is equal to ds. So it follows that dds of r, where s is the arc length, is a unit vector which is tangent to the curve r equal to rs. Of course. So here maybe to emphasize, I'll add another phrase here where s is not any arbitrary parameter but the arc length. So there are two keywords here. One is that dr/ds is a unit vector. Okay, I put that in bold here. Okay, and I put this tangent in bold but in red also. Okay. Now let E subscript S be a unit vector tangent to the curve r equal to rs. Then I can say that ES is ds of r. Of course, if one wishes, I can also say ES is minus of ds of r, because there can be two directions. The vector can either point in the direction of increasing s or decreasing s, depends on which way you go. But there is no loss of generality if I simply say ES is ds of r. Now, if you want the arc length between say P and Q1, okay, then you have to look at this relation ds and integrate it. Okay. So if you want to be very precise, then I say S, the length along the curved path, will be integral from 0 to s. I look at dx ds square plus dy ds square plus dz ds square square root integrated with respect to s. Now, because I've used s as the upper limit of my integration, okay, if I use the same symbol s as the dummy index variable of integration, there will be confusion. To avoid that confusion, I have changed the dummy variable of integration to ds prime. Okay. So these are things which you know from your mathematics course. Let us see what is the relevance of this for this course. Okay. Now, a curve in space is a streamline is a curve in space that is everywhere tangent to the velocity vector. So whatever I talked about so far is for any arbitrary curve. Okay, it could be, need not be a streamline. Okay. If that curve is a streamline, then the tangent to the curve will be the direction of the velocity vector at each and every point. So if a curve in space is a streamline, then we'll say the unit vector Es, which is tangent to the curve, is the velocity vector by its magnitude. So to make it a unit vector, I have to divide V by its magnitude. So we can use the symbol capital V, scalar V, to denote the magnitude of the vector V. So Es equal to V by vector by V. Now this we'll use later on to look at Euler's equations of motion in streamline coordinates. That's why we are talking about it. So at that time, I'll simply write the vector V as a scalar V into Es. Now, R vector, quotient vector equal to R of S, is the equation of a streamline if Es is V by V, or in other words, dr ds is V upon the vector V by the magnitude capital V. Now this is a vector equation which is equivalent to three scalar equations. So if you look at the x component, then the x component of dds of r vector is dx ds, and the x component of the vector V is Vx. So the first equation is dx ds equal to Vx by V. Now if I look at the y component, it will be dy ds equal to Vy by capital V. So if you compare these two scalar equations, on the left hand side it is dds of x, and right hand side you have V subscript x. So simply replace x by y and you get the second equation. Likewise, if it's a 3D case, you will have a third component. So if you look at the z component of this vector equation, z component of dr ds is dz ds, and the vector z component of the vector on the right hand side will be V subscript z by capital V. So in all the three equations, this denominator is the same, and that is actually square root of Vx square plus Vy square plus Vz square. Now I can look at this equation and pull this Vx to the denominator over here and move the ds to the numerator. So I can write the first equation as dx by Vx is ds by v. Okay. Now then the second equation I can get by simply replacing x by y. So I'll get dy by vy equal to ds by v, and the third equation is dz by vz equal to ds by v. So you see that in this set, the right hand side is the same for all the equations. It is ds by v. So that's why you can write the equation of a streamline in this way: dx by vx equal to dy by vy equal to dz by vz equal to ds by v, capital V, where ds is the arc length, increment in the arc length, so root of dx squared plus dy squared plus dz squared, and capital V is the magnitude of the velocity, which is root of vx squared plus vy squared plus vz squared. So you can write the first equation as square root of dr dot dr, and the second one as square root of v dot v, or in other words, capital V is the magnitude of the fluid velocity, which you can call the fluid speed, and the magnitude of dr, the increment in an infinitesimal increment in the position vector of a point along the streamline, will be your arc length along the streamline. Okay, so you would have seen the first three equations dx in a course on any book on fluid mechanics. You might not have seen the last one, that each side is equal to ds upon v. But this will be required when we look at Euler's equations of motion in streamline coordinates. Now the vector form, of course, you can write as dr cross v equal to 0. Okay, why? Because the displacement vector dr is tangent to a curve, and if that curve is a streamline, then the tangent to the curve is parallel to the velocity vector. So dr vector and dv velocity vector, they are parallel vectors, so the cross product is 0. So if you simply look at this, you may see it in some books. You will get the first three equations. If you look at the three components of this vector equation, you'll get dx by vx equal to dy by vy equal to dz by vz. You will not get the fourth one. Okay. So if you say the parametric equation of a streamline is r equal to rs, or equivalently x is xs, y is ys, z is zs, where s is arc length, then you have an initial value problem which you can solve to find the streamlines. So you can write it in vector form as dds of r is velocity vector by capital V. So if the right hand side is known, then you can integrate this equation and find the solutions subject to the initial condition that at some initial value of s, say s equal to s naught, r is r of s naught. And here s naught, of course, could be 0 without loss of generality. So this is a system of first order ordinary differential equations. So in component form, we have three scalar equations, and you will have three initial conditions because they are first order equations. So in principle, if the velocity field is known, you can find out the equation of the streamline through any point. So given the initial coordinates x of s naught, y of s naught, and z of s naught, and the velocity field, you can find the equation of the streamline through that point. Of course, you may not be able to get a closed form analytical result, but you can use a numerical method to find the streamlines. Alright, so in 2D, of course, we don't worry about the z coordinate because we are looking at what's happening at a constant value of z. So you have dx ds is vx by v, dy ds is vy by v, and so we have seen this equation dy dx equal to vx by vy by vx. Okay, and we have answered this question: can two streamlines intersect at a point? Now, this is important, so I'll say it again. Two streamlines may intersect at a point in the flow field where the velocity vector is the zero vector, okay, or the null vector. So such a point is called a stagnation point. And at a stagnation point, all the velocity components are 0. So I called it x subscript s, y subscript s, z subscript s. Okay. So this is the notation for the coordinates of a stagnation point. So the velocity vector at that point must be the 0 vector. So all three components of velocity will be 0. Now let us look at what we may call a relative streamline. So our goal is to solve the belt and turbine problem. Okay. So here we have two coordinate systems, O, X, Y, which is a stationary or fixed coordinate system. And you have a coordinate system which is moving or translating. This is fixed to the vane or blade or bucket of the Pelton turbine. So the translating coordinate system have been denoted by O prime, X prime, Y prime. Now, the parametric equation of a relative streamline as seen by an observer. So we can have an observer whom I have called observer A sitting in the reference frame OXY. And imagine you have an observer B attached to this reference frame which is translated. So what is the streamline pattern that will be seen by observer B? Well, it is similar to what the equations will be similar to the equations that we have already seen. The only difference is now we'll replace x, y, z by x prime, y prime, and z prime. And the arc length parameter s will replace by s prime. So the equation of a relative streamline you can write in the following way: dx prime divided by vx prime will be equal to dy prime by vy prime. And each of these quantities will be equal to dz prime by vz prime. And you can go further and say that these three equations are equal to ds prime by v prime. Now, using primes all the time may be cumbersome. So we'll introduce the notation w for the relative velocity. So we can interchangeably use w, v with the superscript rel, and v prime for the relative velocity. That is the velocity of the fluid as seen by observer B. That is the velocities as measured by observer B. So this will be the absolute velocity v minus capital U vector, where capital U vector is the velocity of translation of observer B, or in other words, the velocity of the origin O prime of the translating frame of reference. And the vector v is the fluid velocity as measured by observer A in the stationary frame of reference. So in this notation then, the equation of a relative streamline you can write as dx prime by wx equal to dy prime by w prime wy equal to dz prime divided by wz equal to ds prime by capital W, where capital W is the magnitude of the relative velocity, and ds prime is an increment in the arc length in the moving frame. So the velocity W you would like to express as a function of x prime, y prime, z prime, and t prime, where t prime is equal to t. Now look at the figure over here.
Sir,
Yeah, any questions?
sir, is this prime coordinates x, y, z you are bringing from the Galilean transformation?
Of course, here I'm looking at the 2D case, so I'm not worried about the Z prime.
Yeah. So for the other one, you are doing from there, right?
In general, for 3D flows, there will be a dz prime by vz prime.
No, sir. I meant to say that how you are relating x prime with x. So you are taking that Galilean transformation.
Pardon, I didn't get you.
Sir, I was telling how are you relating x prime with x? So the primed variables with the non-primed variables. Are you using the Galilean transformation?
The prime variables are measured in this moving frame.
So is that x minus ut?
So x prime will be x minus ut. Okay, let me refresh your memory. I'll open the one of the documents which I had shown last week. Okay. So for the timing, I'll stop sharing this and open the other one. Okay. So last time we introduced this Galilean transformation. So suppose you have a reference frame which is fixed. That's the one in black on the left. Okay. And you have a reference frame which is translating. That is the reference frame on the right. Okay. So I can have a point somewhere here. Okay. I can describe the coordinates of the same point by the triplet x, y, z or the triplet x prime, y prime, z prime. Okay. And for simplicity, we can choose a coordinate system such that this O prime x prime is parallel to x. Okay. And at time t equal to 0, they are coincident. Okay. So you will have x prime equal to x minus ut. But suppose at time t equal to 0, they are not coincident. Okay, then at time t equal to 0, there will be an initial distance between the axis OY and OY prime, which I call x init. Okay. So if you look at it this way, for simplicity, we are taking y prime to be y. We need not worry about z, but in general, there will be a z prime. Okay. So the coordinates will differ only in the x values. Okay. If y prime is y and z prime is z. Now, which is larger, you tell me. If I have a point somewhere here, okay, I'm showing the cursor. So look carefully at the screen, there's a plus cross over here, plus. Okay. So this much value is are you able to see my fingers if I put it here? No. Okay. So which is larger, x or x prime? You tell me.
X.
The origin O is on the left and O prime is right. Okay, so the coordinate x prime will be smaller than the coordinate x. Okay, so x prime is x minus ut minus some initial value, which in the figure for simplicity I have taken to be 0. Okay, so this gives you the relation between x prime and x. Okay. Is it clear? Okay, I'll stop sharing this and go back to the old document. Okay, now is it clear what the meaning of dx prime? So what will happen is, for this particular simple case, we'll not worry about the third equation dz prime by wz because both are 0. Okay, so you will have dx prime by wx equal to dy prime by wy, and wy and vy will be the same, but wx will be vx minus u, and ds prime will be square root of dx prime square plus dy prime square, and w will be square root of wx square plus wy square. Is it clear now?
Yes, sir, it is clear.
Yeah.
It is clear. It is clear.
Okay. All right. So you see this solid surface. This is a section through the vein or bucket, and this is translating to the right with a velocity which we are calling capital U. Okay. So this is an example of what I'll call a relative streamline. That is the inside surface of the bucket. You can call it the wetted surface of the bucket, because the other side of the bucket or vein is exposed to the atmosphere or air. Okay. So you have the fluid on the right over here is air, but on the left of this surface, the fluid is the liquid, which is water in general. Now, this solid surface is an impermeable solid surface, so fluid cannot seep through. So if I take any point on the wetted surface of the liquid, the inside surface of the left surface here, take an area element dA, the volume flow rate or mass flow rate to that surface will be 0. That means that W dot N will be 0. The normal component of W is 0. So if it's an inviscid fluid, then the direction of W will be tangent to the wetted surface. Okay. So if it is tangent to the wetted surface, then that wetted surface is a streamline or a stream surface. But it is what I will call a relative stream surface. It's a stream surface as seen by observer B. So if I denote the coordinates of a relative stagnation point by the symbols x, y, z with a subscript, now capital R, capital S for relative stagnation point. Okay. Then the relative velocity at that point must be 0. So we must have Wx, Wy and Wz all equal to 0. Then we'll call it a relative stagnation point. Now again I have drawn some streamlines over here. Okay, so if you go back to the figure here, the water is coming out of this nozzle. This is the enlarged view. Okay, so this blue streamline here. Okay, so here you have above you have air, below you have air. Okay, and in between here you have water jet which is striking the bucket and it is being deflected. It is deflected because it's an impermeable solid surface. Had it been porous, part of the liquid would have gone through. But here the entire volume is just pushed backwards towards the nozzle. Okay. Due to the symmetry of the bucket or vane, you will have half of the liquid going upwards and half going downwards. Okay. So I've drawn some streamlines over here. Here, this red streamline. So these are all relative streamlines. It will go towards the right, it will turn. So there's some curvature here, and it will go this way and out. Okay. And similarly, if you look at the red streamline at the top, it will be deflected along a curved path and it will go out. Okay. But if you look at the central streamline, it will move in the horizontal direction. We are neglecting the gravitational deflection, and it will strike the point O prime over here. Okay. Now, what will be the relative velocity? Well, the fluid is coming out with some velocity here, let us say Vj, as seen by observer A. So as seen by observer B, the relative velocity of the fluid will be Vj minus u. So somewhere at point 4, the fluid velocity, relative velocity will be Vj minus u. Now at point 1, what is the relative velocity?
Zero.
It will be 0. Okay. So if you look at what is happening, the fluid particle will decelerate as it moves from 4 to 3 to 2 to 1. So Wx4, which is Vj minus u, will be greater than Wx3, and that will be greater than Wx2, and that will be greater than Wx1, which is 0. So this is what we will call a relative stagnation point. So at a stagnation point, I said streamlines will intersect. So here you have an example of a relative stagnation point where two relative streamlines are intersecting. So if this here, of course, I've drawn it in blue. If you look at the tangent to the vane at point 1, that is vertical, that is parallel to OY. Okay. And if you look at the tangent to this central streamline, say that is the line 2-1, line segment 2-1, that is horizontal or parallel to OY. Okay. So now what will happen is there are two tangents. Okay, at a point on the streamline. Now there can be two tangents only if the direction is undefined, that is if the magnitude of the velocity, or in this case the relative velocity, is 0. So by looking at the streamline or the relative streamline, you can identify which is the stagnation point. And if you look at and apply Bernoulli's equation, okay, so I have not yet talked about it. We have to develop the material slowly. Okay, you can show that if you compare the pressure at points 4, 3, 2, 1, where do you think you will have the maximum pressure? Assuming inviscid behavior.
Point 1.
1. Okay, so what we have to do is we have to derive Bernoulli's equation in the moving frame, translating frame. Then only we can argue theoretically why it will be larger. But here you can kind of guess that locally the maximum pressure will be at this point 1. Okay. And if you compare these lines, say CBA, okay, in the direction normal to the streamlines. Okay. Again, I'll show you later on that PA will be larger than PB, larger than PC, because of the curvature. If you consider a fluid particle, there will be a centrifugal force acting on the particle, which will have a direction outwards towards the bend, and that will be balanced by the pressure gradient. So the pressure on the outside of the bend will be larger than the pressure on the inside of the bend. Okay. Now, if you look at in this figure, the black streamline. The pressure at all points on this black streamline is atmospheric pressure. Because why? Because you have air here on this side. Okay. So PC will be atmospheric pressure. Okay. But PB will be larger than PC and PA will be larger than PB. So if you look at the wetted surface, which is on the inside of the bucket or vein or blade, whatever you call it, it will not be, the pressure on the wetted surface will not be equal to atmospheric pressure. It will be larger than atmospheric pressure. And on the other side, you have air. So that is, the pressure on the other side is atmospheric pressure. So because of this pressure difference, the liquid will exert a net force on this solid weight. And that will cause acceleration unless there is a resisting force. So the resistance will come actually from the friction and the bearings, but we are making a model which can predict the work done or the rate of work done. Okay, so we are considering now just one vein or bucket which is translating with a velocity vector which we are calling u, and we'll say that there is a resisting force in the negative OX prime direction, O prime X prime direction, such that the net force on the vein is zero. It is balanced by the difference in the pressure. And if we can find out what is that force, then the power will be that force times the velocity. This is a simplified model. Now in the books that you may see, you can get some e-books or you may have some book on fluid mechanics. All undergraduate textbooks on fluid mechanics will have a chapter on fluid machinery, but only one chapter, and the results they will give in brief. Okay, so here I am trying to explain all the physical observations and facts. Okay, so the subject will become interesting only if you understand the physics. Okay, so what is causing the force? What is the origin of the force on the bucket? Okay, we would like to understand that. So essentially, because the fluid is deflected. Why is it deflected? Because the solid is an impermeable solid. Okay, and because of the curvature of the streamlines, the pressure increases. So the pressure on the inside is larger than the pressure on the outside. So you must understand what is a relative streamline and what is a stagnation point. A relative stagnation point in this case. So this point O prime here is what you may call a relative stagnation point. Okay, so I've indicated it on this figure over here. All right, now any questions regarding this? Now some of these figures.
So could you please explain once again why the pressure on the inside of the vein will be larger?
Why the pressure at which one? B is larger than the pressure at C.
Yes, PA is larger than PC.
Okay. This actually I'll talk about in more depth tomorrow. Okay. For the timing, let me say it is due to the centrifugal effect. Okay. See, when the fluid particle, see, this is the flow will be steady in the moving frame. Okay. Now, when a flow is steady, you know, path lines and streamlines are identical. Okay. So consider a particle somewhere here. All right. Can you see the cross over here, the cursor? It will move along the streamline. It is identical to the path line. So it is moving in a curved path. Okay. So one way to view it this way, when the particle is moving in a curved path, there will be a centripetal acceleration. Okay. So mass of the particle, say dm, times the centripetal acceleration will be equal to the net force on the particle due to pressure. So if there is a net force on the particle due to pressure, then there has to be a pressure difference between two sides of the particle. Okay. So which side will be larger? If you consider the fluid moving in a curved path, I will say this side is the inside of the bend and this is the outside of the bend. Okay. As you move towards the outside of the bend, the pressure will be higher. So the net force due to pressure will be directed towards the inside of the bend. So direction of the pressure force. So consider a particle at point B. Okay. The direction of the pressure force will be towards BC. Net force on the particle due to pressure. And that is what will cause the centripetal acceleration. An alternative viewpoint is to view it as a pseudo force. Okay, you can say that when the particle is moving in a circular path, or a path not exactly a circle but a path with curvature, it is acted on by a centrifugal force. So if you don't have a net force due to pressure in the opposite direction, the particle will fly outwards. Okay, the particle is not flying outwards because the centrifugal force is balanced by the net force on the particle due to pressure. And you can have a net force on a particle due to pressure only when there is a pressure gradient. Does it make sense?
So initially, this red streamline and black streamline. So both of these, before the collision with this Pelton turbine, both of them had same velocity and same pressure, right? All of these streamlines. Hello.
See, okay, let us see it this way. When the fluid is coming out, liquid is coming out of the nozzle, the velocity is, as seen by observer A, is Vj. Okay, as seen by observer B is Vj minus U. Okay, now as a look at the central streamline. As the particle is moving, does the velocity remain the same? It will not. It will undergo a deceleration because it will sense the presence of this obstacle over here. Okay. Since the fluid surface is impermeable, the fluid cannot go through. So if you look at the relative velocity at the point O prime, that is 0. Okay. So if you look at the fluid particles moving from point 4 to 3 to 2 to 1, its relative velocity is decreasing towards the right, and then it will reach a value where the relative velocity is 0. Otherwise, two streamlines, relative streamlines cannot intersect. Okay, so somewhere here towards the left, the velocity is constant, but as it is approaching the bucket, okay, sorry for the interruption. There is a thunderstorm going on. Okay, and my residence is in an area of the campus which is prone to lightning strikes. Okay, so I just switched off my AC. Okay, now is it clear why the velocity is varying?
Yes, sir, that is clear.
If you move along the central streamline. Okay, now if you look at the this red streamline which is moving in a curved path. Okay, here also there may be some changes. Okay, so to find how the velocity varies, then you have to solve Euler's equations of motion along with the continuity equation. Okay, which is not easy because they are nonlinear differential equations. However, if you look at the equations, you can, which I'll derive tomorrow. Okay, we can explain why the pressure might increase in certain directions. Excuse me. All right, so both the pressure as well as the velocity can vary from point to point. Okay, but if you are very close to the nozzle, somewhere here, then the pressure might be constant and the velocity might be constant. So if you look at what is happening inside the jet, if you see the streamlines as straight lines, okay, then you can assume the pressure distribution inside the jet to be atmospheric pressure, which is the pressure on the outside of the jet. Okay, so at the exit point here, after it has come out, we can assume the pressure to be atmospheric pressure, and here also at this exit. But somewhere in the middle here, where you see the streamlines moving in a curved path, okay, the curvature will induce a pressure gradient inside, which is not balanced by gravity. Okay, so there's an additional pressure gradient due to the curvature of the streamlines, and therefore it is not correct to say that everywhere inside the jet the pressure is atmospheric pressure. Is it clear now? I'm just stating the fact right now. I'll explain in more detail tomorrow after I derive the equation. Or any other questions? Okay, it is almost 2:55 now. Okay. So what I'll do is I'll end here today. Okay. And tomorrow again at 4 o'clock, I'll resume my lectures.
So can you share today's slides?
You want the slides?
Yes, sir.
Okay, okay. So tonight I'll upload it so that you can look at it. Okay.
Sir, please upload the previous ones also.
Yeah, I upload everyone, all the slides. Now, as I mentioned, I want to number them in a logical sequence so that it becomes easier for you to refer to. And if you have a discussion also, you can tell me what is the number of the document.
Yes, sir. Thank you, sir.
Okay. Now, any other questions? If not, then I'll stop here today. Okay, thank you.